Welcome to Session 3 of Intro to GameTank Programming. Today we'll be covering the sound system of the GameTank, called the Audio Coprocessor. The Audio Coprocessor is a second 6502 computer within the console that produces sound and music one sample at a time. That's sample as in a single voltage, not as in a sound clip that gets looped. The ACP uses a memory map that is shared with a portion of the main system. At the start of a game, this memory needs to be filled with a program. Then, to produce game audio, the main system modifies parts of the shared memory to communicate with the ACP's program. The ACP program computes an 8-bit value to write to the digital-to-analog converter each time an interrupt is received. These interrupts are produced by a timer circuit, so the DAC is repeatedly updated at a steady rate. By the way, here's a quick aside on terminology. The chips that run game code and audio code are both the W65C02S from Western Design Center. Both are microprocessors and act as the central processing unit of their own computing section. But, in this video, when I say CPU, I'll be referring to the processor that executes code directly from the cartridge. And when I say ACP, I'll be talking about the processor that will generate audio samples. This diagram illustrates the memory mapping for the ACP as well as its control registers. The shared audio RAM is located from hex 3000 through hex 3FFF from the CPU's perspective. On the ACP side, this RAM is always selected regardless of the four most significant address bits. Therefore, the 4 kilobytes of audio RAM are looped as you move up the address space. Reading from hex 0123 is the same as reading from hex 1123 or hex F123. The same idea applies to writes as well, but with one extra effect. If the ACP writes to an address at hex 8000 or above, meaning the leading bit is a 1, the DAC buffer register will be updated. In addition to the shared RAM, the main CPU can also use addresses hex 2000, hex 2001, and hex 2006 to control the ACP's reset signal, non-maskable interrupt, and sample rate respectively. The reset signal functions for the ACP much the same as hitting the reset button on the GameTank. When the CPU writes to hex 2000, the ACP will drop what it's doing and jump to the start of its reset handler. This will be used after loading a program into the audio RAM to initialize the ACP. The non-maskable interrupt allows the CPU to trigger a function to run on the ACP immediately. The ACP will remember what it was doing beforehand and resume that activity after executing a return from interrupt instruction. This can be useful for notifying the ACP that some data has been modified and is ready to consume. Finally, the sample rate register controls the timer circuit for generating IRQ events. While the reset and NMI registers discard the value written, the sample rate register uses the lower 7 bits to determine how many ticks of the main 3.5 MHz clock lapse between DAC samples. A higher value will mean a lower sample rate, but also allow most processor cycles for computing each sample. The slowest sample rate is approximately 14 kHz. And because the ACP is clocked 4 times faster than the CPU, it allows for 1024 cycles per sample. The highest bit of the sample rate register is connected to the ACP's ready bit. Setting it to 0 will put the ACP into a wait state, thereby suspending its operation. This should be done while initializing the ACP's program to prevent unpredictable behavior. Now, let's outline what your GameTank code needs to accomplish to produce sounds. Everything above the line typically happens just once at boot, while everything below the line happens very often as the game runs. First, we suspend the ACP so that it doesn't accidentally modify the program while we're loading it. Then we extract or copy the program binary into audio RAM, ending at hex 3FFF. Finally, we trigger a reset and then unpause the ACP. When we want to control the ACP program from game code, we write to the shared memory and alter the parameters of the sound code. If we want to make sure that the ACP doesn't act on partially updated parameters, we can set aside a buffer in shared memory that only gets read during the NMI handler. The NMI then acts as a signal to read and process the complete set of updates. The previous slide showed the CPU's role in making sound, but what about the ACP? Well, its job is typically a lot simpler. Most of the code in an ACP program will likely be in its IRQ handler. When the IRQ handler runs, it computes a single sample and writes it to the DAC buffer. Because the time to compute a sample may vary, the DAC buffer is copied to the actual DAC when the next IRQ signal arrives. This prevents jitter, a variation in sample rate, without having to worry about it in code. Here's an example ACP program. It tracks a 16-bit counter labeled as wave state, L for low byte, and H for high byte. Every time a sample is computed, the 16-bit wave rate is added to wave state. Then the high byte of wave state is copied to the DAC buffer. As the wave state is incremented, it rises steadily before rolling back over to a low value. This produces a sawtooth-shaped waveform known for its characteristic buzzy or harsh sound. The program is written in its own assembly file and compiled to a separate binary. Because the example ACP program is so small, it's very simple to load. This assembly code defines a subroutine that copies 256 bytes from the ACP code label to the last page of audio RAM, starting at hex 3F100. The .incbin directive is used to include the ACP binary, similar to how sprite data was included in the previous tutorial. It's important that when copying the program to audio RAM, the data is aligned to the end of audio RAM because that's where the ACP will look for the reset, NMI, and IRQ vectors. This subroutine also includes pausing and unpausing the ACP, as well as setting the sample rate. You can call it before the start of your main loop. To control this ACP program after it's loaded, you'll write to the wave rate addresses. A higher number will result in a higher pitched sound, while rating 0 will stop the sound completely. For the ACP, wave rate is located at hex 03 and hex 04, but for the CPU, we must offset these values by hex 3000 to target them within audio RAM. In this example, we modified the vertical collision detection routine, so if the player hits the bottom barrier, we'll store the value 8 into wave rate H. If no collision occurs, then we store 0 to silence the sound. This should result in a sawtooth that repeats every 32 samples and produces a 437 Hz tone, which is just slightly flat of middle A. Note that we've skipped over the use of NMI for now to keep the example simple. Now we'll build the code, running VASM once for the ACP code, and then once again for the main game code. The ACP code should be built first, otherwise the binary the main game code imports won't exist and you'll get an error. There's the sound as we hit the brick wall. The tone isn't continuous because the collision code moves the player away from the wall and on the next frame silences the audio. Then, as we keep holding the down button, the sound returns on the frame after that. If we modify the ACP code and create a larger binary, we'll have two problems to deal with. The first is that the example loader shown earlier only works on 256 bytes at a time. The second is that a larger ACP binary competes with other assets and code for space. We can mitigate both these problems at once by using inflate to load our audio code, much like how we load sprites. The code shown here comes from CubicleNight and loads a larger, more complex binary that computes multiple audio channels. Another detail I've glossed over is the use of NMI to alert the ACP of parameter changes. Because we were only setting 1 byte at a time, we were able to get away with directly writing the same memory that the ACP's IRQ handler reads. If your ACP program includes several parameters you might change, then you'd want to place them in a buffer and update all their values atomically. This excerpt is from a Cursed Fiend's ACP program. When the NMI is received, the program alternates between reading a 1 byte address and a 1 byte value until it reads an address of 0. All of the parameters live on the 0 page, so this can be used to update only the changed parameters and not loop over every address every time. To recap the process for adding audio to your GameTank game, you write code in an additional ASM file that computes a sample in its IRQ handler. Your main game code loads that binary with the end aligned to hex 3FFF. The reset, NMI, and sample rate registers along with shared memory allow you to control the ACP from your main program. Thanks for following along with this episode, and as always, feel free to ask questions on the Discord server or in the comments here.